In this lesson, we're going to discuss the reflective property of parabolas. We have 3 vocabulary words to discuss, and then we have the actual reflective property of parabolas and an example. So here is our first vocabulary word, a focal chord. This is where you have a line segment that passes through the focus of a parabola and has endpoints on the parabola. And this is what a focal chord is. So let's take out our patty paper parabola and draw in examples of a focal chord.
All right, so here was the patty paper parabola that we created in a previous activity, and I just traced that exact same parabola onto a new piece of patty paper so that I could keep my original and show you what a focal chord is. So a focal chord is the following. If I take, here's my focus, and I draw a segment that goes through the focus but then has endpoints on the parabola, I have just created a focal chord. So if you remember a chord from geometry, a chord it was any segment whose endpoints were on the circle. So a focal chord is a segment that has the endpoints on the parabola going through the focus. So I could do this as a focal chord. I could do this as a focal chord. I could do this as a focal chord. You're probably getting the point here, that if I draw any segment through the focus to the other side of the parabola, each of these are considered a focal chord.
Parabolas also occur in a wide variety of applications. For instance, a parabolic reflector can be formed by revolving a parabola about its axis. The resulting surface has the property that all incoming rays parallel to the axis are reflected through the focus of the parabola. This is the principle behind the construction of the parabolic mirrors used in reflecting telescopes. Conversely, the light rays emanating from the focus of a parabolic reflector used in a flashlight are all parallel to one another, as shown in this figure. The specific focal chord perpendicular to the axis of the parabola is called the lattice rectum. Let's use our patty paper again to show how this is formed.
Okay, again, here is the patty paper parabola we created in a previous activity, and I went ahead and just traced over it so that I could draw our next vocabulary word, which of course is my favorite to say. I'm actually kind of glad I get to say it in a video and not in front of you in class, but it is the lattice rectum. And so in the previous patty paper, we looked at focal chords, and a focal chord can just be any chord where the endpoints are on the parabola going through the focus. But the lattice rectum is this one. If my axis of symmetry is going through the focus and the vertex, the lattice rectum is the focal chord that is perpendicular to your axis of symmetry in the parabola. So this is my lattice rectum.
So now let's talk about what it means to be a tangent line. And this is definitely a precursor to the calculus we'll be learning in just a couple months. A line is tangent to a parabola at a point on the parabola if the line intersects but does not cross the parabola at the point. Tangent lines to parabolas have special properties related to the use of parabolas in constructing reflective surfaces. Again, let's take out our patty paper and look at what a tangent line would look to that parabola.
Okay, again, starting with my patty paper parabola, and again, I traced it so that we could draw our last vocabulary word, which is a tangent. So here's what a tangent looks like. If you take any point on the parabola and you draw a line that touches it once but does not cross through it, then we have just drawn a tangent line to the parabola. So this could be a tangent line. This could be a tangent line. I can draw the tangent line through the vertex. This could be a tangent line. This could be a tangent line. Again, a tangent line is a line that touches an object once. So if you put together all of these tangent lines together, you can certainly see how it's going to make the shape of the parabola.
So let's talk about the reflective property of a parabola. It has to do with this tangent line. If you have a tangent line to a parabola at point P, which we have right here, it is going to make equal angles with the following 2 lines. The line from your point of tangency to the focus, and your line from the point of tangency to the axis of your parabola. So since those 2 angles are congruent, what you end up with is an isosceles triangle. Therefore, you know that this distance here is congruent to this distance here. Let's do an example problem to show how this is used.
For our last example, we're going to find an equation of the tangent line to the parabola at the given point, and we're going to find the x-intercept of the line. So we're going to use our reflective property of parabolas to answer this question. So if I have y equals negative 2x squared, I know that I have a vertex at 0, 0, and I know that this is going downward. Now, here's my vertex, and 2, negative 8, and I'm just going to go by 2's, 2, 4, 6, 8. So here is my point of tangency. So this is my P, or my point of tangency. All right, what the reflective property says is, if I draw a segment from the point of tangency to the focus, that it's going to create the same angle from the point of tangency to another point up here. So let's first find the focus. So if I put this into standard form, I'm going to multiply both sides by negative 1/2. So this means 4p is equal to negative 1/2. So my p value is going to be negative 1/8. So this means my focus right here, my focus, is the point 0, negative 1/8. So by the reflective property of parabolas, if I draw a segment from F to P, the focus to the point of tangency, then it's also going to create an angle up here that is congruent. And if these two angles are congruent, it means that this distance here and this distance here are congruent. So what does it mean that I have to do? I have to find the distance between the point of tangency and my focus. So that's the distance formula. So again, my vertex is, my point of tangency is 2, negative 8, and my focus is 0, negative 1/8. So I have to do the distance formula. So I can take the difference in the x's and square them, plus the difference in the y's and square them, and that's going to cause that to be positive. Here is going to be the arithmetic in order to find that distance.
So here's our work to do some of that distance formula. I get it that you could probably just shove it into a calculator and have it come out, but I want to show you the steps because we want our answer to be exact, not a decimal approximation. So if you look at the setup, we want to do the square root of 2 squared plus the quantity negative 8 plus 1/8 squared. 2 squared is 4, pretty straightforward. But then negative 8 plus 1/8 is negative 7 7/8, which as an improper fraction is negative 63/8. Okay, so I simplified the negative 8 plus 1/8 to negative 63/8. Next, you need to square the negative 63/8. So when you square negative 63, you get 3,969, and when you square 8, you get 64. I still have to add that to 4. That requires a common denominator. So when you get your common denominator and you add the fractions, then 4 plus 3,969/64 is 4,225/64, both of which are perfect squares, and so this simplifies to 65/8.
So now what you saw from that arithmetic is that the distance is 65/8. So this distance is 65/8. So that means this distance from this point here to the focus is 65/8. If I want to find this coordinate, however, I have to take off this distance of the focus that's right here. So I need to take 65/8 and subtract 1/8. So that means the distance from this point to the vertex, which is at the origin, is 64/8, otherwise known as 8. So now in order for me to find the equation of a tangent line, when you find the equation of a line, you need two things. You need a point and you need a slope. Well, I've got 2 points, and that can help me to find my slope, and I already have my y-intercept, so life is good. So to find the slope between those 2 points, I take the differences in y's over the differences in x's. So I get 16 over negative 2, which is negative 8. The negative should make sense because this line is negative. And so my y-intercept is 8, so I have y equals negative 8x plus 8 as the equation of my line. Now they also want me to find the x-intercept. Well, to find x-intercepts, we let the y be 0. Put negative 8 over here by subtracting 8 from both sides. Divide by negative 8, so x is 1. So this point right here is 1, 0. So find an equation of the tangent line. Y equals negative 8x plus 8. And the x-intercept is 1, 0. So now you are ready to finish the assignment on conic sections relating to parabolas. And so starting on page 637, I think it's actually starting on page 638. But please do problems 49 to 61, the odds. Good luck.